Welcome to the last talk of today in this room at the 20-year anniversary of FrOSCon. I am really proud to be here, very thankful to be invited to have a talk. We will discuss provisioning stuff, we will discuss provisioning Kubernetes in particular, but in a very special way. For all of my demos, I will use Flatcar Container Linux. That's because I'm a Flatcar maintainer. We are a third-party, community-driven operating system, Linux distro, tailored to run container workloads. We're in the CNCF, so if you doubt my assessment of being independent, that should kind of secure it. And yeah, so the first thing I want to show you today is what the systemd-sysext, a systemd system extension is, how it is image-based, how it is immutable, and how you can't fiddle around with the bits there, how you ship it, how you install it, how you update it. This will happen to include Kubernetes by chance, because I put it in there. The third demo will then actually jump on provisioning an actual Kubernetes cluster locally here on my machine. And the fourth one will be about in-place updates of Kubernetes on these clusters without interfering with the cluster workloads. But let's start from the beginning. Thilo, start provisioning the ClusterAPI cluster. And this is where Azure comes into play. So I'm going to use Azure for the fourth demo. I work there. I can use this for free. I don't try to pull you on Azure. Use whatever cloud you can use for free for this. If you operate large clusters, OpenStack works very well with Flatcar, for instance. All right. So we will just kick this off, and the reason I need to do it the fourth demo before even starting the first is it can take a bit of time. Provisioning a full-blown Kubernetes cluster on Azure. So we will just start this, and then we will go back, and we will take a look every now and then in how our fourth demo is doing. All right, we created, this is using ClusterAPI, which provisions Kubernetes clusters from Kubernetes clusters, and that's why their kind of mascot is a turtle, because it's turtles all the way down. And we have now a local kind cluster that runs on this machine, and I will use it to provision a full-blown Kubernetes cluster, not using AKS, but just using Azure Virtual Machines on Azure. All right, while we're waiting on this, I need to steer my little patch lines because no YAML is perfect. And we need to add 2 fix-ups to make the thing really enjoyable for us.
Can you show the ClusterAPI configuration?
Yes, we can look into that, and at the fourth demo we'll dive into that. And that's not the part that takes time, but okay, that worked. And now we want this, and that worked too. And now we can actually provision a cluster, and that's this automation. And this will populate this resource group later on with all that we need, but it'll take a while. Okay, let's start from the very beginning. I've promised we're talking about systemd-sysext here. This is a way to ship software in a file system container. To give you a kind of visible example, let's assume we wanted to ship a full Kubernetes, including all configuration, including the systemd units to start it, basically as a full package. Then we could do that with systemd-sysext using this file-based approach. If you check what this actually is, then it'll tell you that looks like a squashfs. And that's because it is. And you can mount it. Now, and that's why I have the little Midnight Commander directory view here. If you check this out, this looks like a regular Linux file system, but it has very few files, right? So we see kubeadm, kubectl binaries in bin. We see some systemd configuration in userlib. In libexec, we find just a symlink to the volume plugin, which kubelet puts into var. So it needs that in order to be happy. And then in user local, we see the CNI part, and basically the low-level bits of the Kubernetes CNI. So this includes a full-blown Kubernetes, but not more than that. So it's just the Kubernetes bits, the Kubernetes configuration, and some weird systemd stuff, right? What is this? Now, this is the kubelet service. So kubelet actually starts when we ship the whole stuff. And the way we make kubelet start is kind of a like twofold magic. The first is we add a systemd drop-in for multi-user target, which adds a dependency to kubelet. So multi-user target should include having kubelet started. And then in the systemd-sysext metadata, which is the only thing that is like divergent from any regular file system that you would see under Linux, we just say ID would usually be the operating system version. We don't care about that because Kubernetes ships static binaries, so we run in any Linux, any version. We just need a kernel. We ship an architecture, and we tell systemd to please reload all of the unit files after that file system image, which I just show you, was merged. So this takes care of starting those kubelet units that I showed you earlier. Now, combining this with Flatcar's way to basically configure and provision stuff before the instance actually comes up, we can create a very simple Flatcar configuration. So this is what you feed into a Flatcar instance when it is booting, and it runs at very first boot from the init to kind of lay out and render your system. It only runs at first boot, so we don't need to care about reboots because it's guaranteed to only be executed once. So what we tell Flatcar here is go to this source, take this file via HTTP, and put it here. And we'll take it from there manually because that's the first demo where you just need to be, get accompanied to sysext and grow an understanding how the whole thing integrates with systems. So this isn't automatically applied. It will not be part of the file system when we deploy it. It will be lingering there until we start working with it because, again, that's the first demo. This part here for completeness tells Flatcar to please deactivate automated updates. Flatcar ships with in-place updates, and I don't want my system to update the virtual machine that I use for a demo while I'm doing the demo. So it's nothing to do with the actual sysext provisioning, but it needs to be there in order to make this demo work. Okay, now in the cloud-native world, we have this ritual that needs to be adhered to, which is transpiling YAML to JSON, and that's what we're going to do here. Because the Flatcar provisioning logic only understands JSON, and humans only understand YAML. So I just generated the JSON file from that YAML file, which basically contains the same mechanisms just in JSON, so Flatcar can eat and validate it. All right. Let's proceed with the demo. Now, I have the Flatcar QEMU release right here, and that's pretty straightforward. It's just a bunch of QCOW2 files. One of them is the Flatcar base image, and that's a whole disk image with the system partition and all of the partitions in it. It's never been booted. We're gonna boot it for the first time, and that's kind of important because, you know, the configuration we're going to supply only applies when we boot it first, when we boot it once. And here we go. I need to start a web server because I told Flatcar, go fetch this file from that web server. So here we go. And we should see Flatcar reach out, fetch that file, and it just did that. It actually stops booting at the init RD and frantically tries to fetch its files. And it'll do that again and again and again until either it runs into a timeout and provisioning fails, or it finds that file, which is beneficial for my demo. Okay, so we didn't do any magic here. We just dropped a file here. There it is. Systemd doesn't know about it. We just put, it could be any file. Now, the next thing we're going to do is we're going to tell systemd, by the way, there's a new system extension which just dropped. And it's there. So please show it and use it. But before I do it, I will try to, by the obvious basically, I try to run kubelet. It's not there. When I check usr bin, there are no files that match this, no kubelet, no nothing. And now I will, let me see if I have this pastable. Oh, in the old demo, I actually mounted the sysext and explored the file system, which I've done on my host system, because Flatcar doesn't ship the Midnight commander, but my host has it, so we can interactively explore the sysext. All right. Oh, look, I'm doing a systemd-sysext list here before that as well. So I could basically show you the files that are the sysext that are known to the system. And you even see a few sysext listed here. And the reason for that is that Flatcar makes heavy use of sysext. Even the core system uses, in this case, 3. So you can switch on and off functionality, and when you switch it off, it'll disappear from your file system. Now, I will just symlink the sysext file into a place that systemd-sysext knows about, which is etc extensions. And if you check out etc extensions, then you will see the other sysext files there, right? In that case, the ones we've shipped and the Kubernetes one we just automatically provisioned. And now systemd-sysext list will show us there are now 4 sysexts. So it recognizes Kubernetes, but if I get the current status, it only says that there are 3 sysexts merged, and that is because it doesn't auto-merge anything. It just wants confirmation from you, the user, that it actually acts on a sysext that it newly detected. So systemd systemctl reload. I just reload the service, which refreshes the list, and then we see 4 sysexts merged. Very young version. You can actually run kubelet because it suddenly appeared in the file system. So that's what sysext does. You ship stuff readily laid out in the file system that you want to have appear in your server. You ship activation units that start stuff automatically when you merge it, which is the case, right? Somewhere here there's kubelet being very sad because all of the kubelet config is missing because we don't deal with actual Kubernetes yet. And the benefit here is you basically have like a full kind of package that you can create. You don't need any active code on hosts that do things that need to be reverted later. You can ship a static file system image and do everything from there. And let me check if I have anything in my notes to show you. No, that's it. So that's basically how you ship sysext, what actually is a sysext, how you ship it, and how you use it. Now, having these applications in file system images, self-contained images, that do not leave any traces on the hosts when they are unmerged and deleted, does have some benefits when you think about versioning, updates, and software lifecycle, and that will be my next demo. So in this demo, let us actually have a look at the big cluster first. There are all these little resources being generated. That's good stuff. So this is our full cluster. I think 7 nodes or something. Yeah, and it's done. We get to the cluster. We get back to the cluster later. There's a complementary service shipped with systemd. Oh, basically, this feature, systemd-sysext, is probably on all of the Linux distros you're using if it's systemd based. It's been shipped since systemd, I think 2.4.2 or something, stuff that goes back 4 years ago. So you do have the binary systemd-sysext on your system. You probably never heard of it. It was targeted at immutable distros like Flatcar at the beginning, but it's since been extended to cover general purpose distros as well. sysupdate, all right. So as I said, there's a complementary service called systemd-sysext, and also we will go a little further in our configuration. So what we're going to do is we won't just put the sysext to opt extensions. We will also generate a symlink, which we did manually in the first step, just to give you an idea of how sysexts are being merged into the system. In this step, automation will do that for us. And automation will also download an additional file. And this is what sysupdate needs to act on. So in this file, which is in the web server, obviously, because it needs to be served. Let me actually stop this demo's web server, or we'll get conflicting ports. That's a sysupdate config. It just tells sysupdate to please check this URL for updates. And we're going to do in-place updates of Kubernetes manually, really step by step in this demo. All right, so you've seen the YAML file. We're basically automating our whole first demo, and we're adding an additional sysconfig file. Now, I already transpiled, but you know, because it's a retro in the cloud native world, here we go again. Transpiling YAML to JSON. And again, in the Flatcar VM directory, I'm gonna do the magic command line. It's pretty much the same as we used before, but since I learned from my first demo this time, I will actually run the web server before I start Flatcar. All right, let's start this snapshot. And now we can basically check this to just see how fast this actually works. The Kubernetes sysext is a few dozen megabytes, so it's not really big. And you know, if you do this in any other environment, this is the first boot where it renders the whole, basically the whole operating system image. And it's still that fast, because we focus on one thing only in Flatcar, and that's running containers. And that allows to take some amazing shortcuts. All right. Now, in the instance, we see kubelet actually already being there. So the sysext was merged successfully. And, oops. This is the fun part when you're actually interacting with the serial console with your virtual machine. You get kernel messages. So you see that the symlink was created by our provisioning software. It goes here. And now the additional thing that we did, right, is we deployed this sysupdate config. Now, just to basically show it to you. In our provisioning directory, we only have a single sysext right now, and that's where the symlink points to now. If we, no, I don't want to split screen, that's too small. If I go into the web server directory, which has the sysext image, you see two images actually. It's version 131.0 and .3. And in the update conf, it just checks for 131. Something. So sysupdate is semantic version aware, and it can actually understand versions. It's not going to go and use a directory listing of your web server. Instead, it'll look for that file for SHA-256 sums. And you see the file names here at the very right. Of course, the checksums need to match after download. But this is basically what systemd-sysext will go and fetch. And this is how it will understand that there's a new version of that sysext available. I'm going to go back to the demo and start the update. Now, systemd-sysext is meant to be run from a timer unit, so you're not meant to actually type this. And I deactivated the timer unit for demo purposes. So you see it never ran, it doesn't have an entry in the log. And now I will do what the timer unit will actually normally do. I will just start it. And you see that it was blocking for like a small moment, and in that very moment it basically did all the work. And it's fast because I use a local web server. So you see it's pretty noisy when it actually has some work to do. And it tells you that, you can't see it. It tells you that it found a SHA-sum. It tells you that, oh look, there's a new version 3 for a sysext I am meant to control and update. I'm gonna go fetch it. And then it goes and fetches it, and it puts where we told it to put it in opt extensions someplace. And you see there's 2 files now because it updated. And then there's other work to do, right? We need to tell systemd-sysext that there actually is now a different version, and that's easy. Because this is a symlink. So Kubernetes now points to version 131.3. Now, when I run, kubelet --version, which version do we see? Right, this with an N. We see the old version. Why do we see the old version? Because again, systemd doesn't want to break your stuff, no matter what other people might be claiming. It actually leaves you at this point because you staged the update for Kubernetes, but you might want to do additional actions before you apply it. We could apply it by rebooting, because then in the initial boot, the new symlink will be picked up and the stuff will be merged, or we can just reload the context of that service. Oh no, it's the other way around. Reload systemd-sysext. All right, and now we have version 131.3. So we in place updated Kubernetes. Yes, please.
Is it possible for systemd-sysext?
Yes, yes, that is possible. Oh, sorry. The question was whether it's possible for systemd-sysext to automate that step and basically do it all by itself. Yes. With additional systemd units that you can ship either via sysext or via your regular system, you could even shut down the related services because you don't want to, just switch the binaries while the service is still running, and then after successful merge, bring them back up again. Yes, that's absolutely possible. All right, and this is. So we've seen what a sysext is, and this is how a sysext is being updated. Okay. Third demo. And this time we actually do Kubernetes stuff. If you came for Kubernetes, now is the time where things get interesting. Thilo applied a QOD YAML. Yes. So we have this nice we have this nice Kubernetes cluster, the big one deployed with ClusterAPI running and ready. And I did all the stuff that I showed you, and I did the stuff that I will show you in demo 3 on these nodes entirely automatically. Now my point here is what I can do now, which I also need to do, you know, kind of staged because it'll take some time. I can instruct a Kubernetes operator to act on information which we'll see in demo 3 and refresh nodes. We use QD here for node refresh. QD is amazing. And I'm gonna put this watch up so we can later check the version of these nodes. Right now we will remember that all of the nodes run 1.30.0, and you can see my demo is pretty old here. I need to update it to a version that's actually supported. So all of the nodes run that version. But now for the nice Kubernetes stuff. All right, so we've seen how we provision Kubernetes, how we update the Kubernetes bits, but we haven't seen yet how we actually configure Kubernetes and make it an actual workable cluster. This demo will be very confusing because I will be using a lot of shells in that screen. If you can't follow, tell me to stop. I'll go slower and try to go into details. All right. The first thing we're going to provision is the Kubernetes control plane node. This is the API server which you talk to with kubectl, and this will orchestrate all of the pods of the worker nodes for us. This is a somewhat slightly more complicated deployment. I've written basically the code that I use for that deployment here. We will use the JSON of the YAML file. I'll show you in a second. And we will add a second network device, virtual network device, to QEMU. With that network device, all of my 3 nodes will be interconnected within their own private net. It's like a second network card that has a cable for all of them. We will also use snapshot mode, which I've been silently using during all of the demos. Snapshot mode is amazing because it keeps all changes made to a virtual machine in memory. It never writes it to the actual disk file on disk. The beauty of that is that you can start the Kubernetes control plane at as many workers as your machine can handle based on the very same file system image. Base image that we use. And this is neat for demos. It's no regrets Kubernetes. You can actually wreak havoc in that Kubernetes cluster. No one cares because if you shut everything down and boot it back up again, it'll all be pristine again. Okay. I will actually start the control plane node before we go through the YAML. The reason for that is it takes a little bit of time because it needs to populate, the CNI needs to deploy, and all these things that Kubernetes needs to do. Yeah. So the command that you've seen in the README markdown, I actually have a small wrapper script around it, and that's basically the same thing you've seen in the README because I don't want to copy paste it. So I'm going to start this, and then it is a Flatcar VM still running. Yes. Yeah. So my previous demos, Flatcar VM was still running, so there was a port conflict. This is why I love live demos. The exciting stuff. All right. So this is slightly more complex because we are adding to the config of the second demo, which added to the config of the first demo. There are some old friends here. There's our sysext. There's our systemd-sysext configuration, which in this case will apply automatically. So I actually activate the sysupdate timer. So it'll just go fetch and stage my update. And this is the second network card, local network broadcast bus communication that VMs will later use to actually form the cluster. So that's not really related to Kubernetes. It's just some flat car automation to use that nice virtual hardware that we defined. I also set a host name because the control plane needs to resolve its own name, otherwise Kubernetes will fail. And so here's the sysupdate timer, and I set it to active. And I actually have a very aggressive schedule because I don't want to wait for an hour for systemd-sysext to wake up and then find the update. This is the beef of the Kubernetes configuration. Here I tell Kubernetes, oh no, wait, this is the systemd-sysext stuff. Here's the beef of the Kubernetes configuration. Here I tell kubeadm to basically roll out the service. I add a few command line parameters so it can start, and I deactivate the internal timeout because that got me into trouble with previous demos. There's a drop-in for kubelet as well, where I tell it its internal IP, so it basically can act on that, and this will get the cluster up and running. All right, the thing we want to do now is we want to go and grab the kube config that kubeadm will drop for us on the worker node, on the control plane node, and there it is. And then this will be used with kubectl to actually interact with the node. So we see there's only one node now, and it's not ready. It's not ready because we don't have deployed the CNI yet, so it can't get its networking ready, and DNS doesn't work, and it's in a bad shape. But this is a manual step-by-step thing for Kubernetes. So that's why we do it this way. Okay. And here it is. As a CNI, we'll be using Calico, and Calico is nice enough to provide its application YAML in a GitHub bucket, so you can just go and say, go grab the Calico YAML and just do the right thing in your node. Okay. So depending on the Wi-Fi, because this needs to download stuff, obviously, oh, it's ready. Oh, wow, the Wi-Fi is awesome. I've never seen it be ready that fast. This is amazing. So the node is ready now. We have a working CNI and a working control plane node. We can now politely ask the node to tell us the command that we would need to add to the worker nodes to join the cluster. Now, it gets the IP address slightly wrong, but we don't really care about that. We care about the token and the discovery token here. And so now I'm doing something for my development cluster that you should never do in your production clusters. I will go into the node configuration here, and I will just paste secrets there. Don't do that. Do it for development, it's awesome. Don't paste secrets into your node configuration when you run stuff in production. Worker 2 needs the same. All right. And you see, previous tokens there from previous demos that I did. And now because we touched the YAML, we just transpile it again. And now, this is this is where we look into, this is our control plane node. And here's where we transpiled. So I will open the demo here once again. And go here. And so I have wrapper scripts for starting the workers as well, right? And this works slightly similarly to how we started the control plane. Again, custom networking configuration, and it uses the respective worker node JSON for provisioning. So this is gonna boot, and this is where we really benefit from the snapshot mode, because we can. I could create 20 more workers if my machine would be able to take it. It's not. So this is what I do. Get nodes. Okay. We see the workers slowly coming up. And so the CNI needs a little bit to actually, go to the workers and also cover the workers, and you see them coming up, and you see them also slowly getting ready. And this is actually a very nice throwaway Kubernetes cluster for development use. You can script that, you can automate like all of what I just told you, right? But the reason I'm using it today is, where's my README? Here. We're here to check how to in-place upgrade Kubernetes, right? And so I'm going to do that right now. So let me find worker 1. On worker 1, all the stuff we did manually in the last step has been automated. So if I check etc extensions, the symlink already points to the new version. And the new version has already been downloaded. So systemd-sysext update was already active. However, kubelet is still on 131.0 because this is the point that we want to do here, that I want to show you interactively. Now, I told systemd-sysext update to, when an update has been downloaded and staged, to please go and create a file for me. That file is in run, and it is called reboot required. Now, if you've used node refresh operators and node reboot operators on Kubernetes, you recognize this pattern. Because node reboot operators like QOD, which I deployed to the larger Azure cluster before, they check for that file. If they find that file, they will mask that node, they will unpopulate it, they will reboot the node, they will uncordon the node so the pods all come back, and then you have in-place updated entirely automatically. Like no user intervention needed. This will not happen here. I'll do something scary. I'll do this. So I'm QD now. I have depopulated the node. The node is good to be rebooted. Now we check the output here. And we will see after a very short while that we've in place updated that Kubernetes version. This is a lot faster than deleting the node and recreating the whole node. It's also a lot less risky. And we could go through that. Oh, this is worker 1, it's done. And, sorry, sudo make me a sandwich. This is done. This can be done for all nodes. So now here, that's updated. And the scariest part, of course, because this is not a redundant control plane. I only have one. Yeah, go ahead. The downgrade way is, in my setup here, manual, but you can as well. Okay. To be entirely fair, I'm not even sure whether upstream Kubernetes supports downgrades, but we're talking about sysext here, not about upstream Kubernetes, so just go for it. So we're just using the .o, and we're recreating the etc extensions Kubernetes symlink, right? So I'm overwriting permission denied. Yeah, because I'm not root. Sudo please. Okay, it did that. Now, I don't want to go through a second reboot, So I'm just gonna, I'll just, oh wait, maybe this. So which worker was that? We're on worker 2. Worker 2 has very clearly that version of Kubernetes. Oh, I need to go through a reboot. I need to go through a reboot because that won't automatically restart kubelet. We could actually do soft reboot, which is a thing with modern systemds where it just stops all user space stuff and then starts all user space stuff again. And there we rolled back. But thank you for the question. That's actually, this is awesome. This is why I like, yes, please.
Let's say we want to do this automatically.
Yes.
How do we ensure that not all the workers are rebooted or updated in the same second?
It shouldn't. What you should actually do is, and this is where QD comes in. So your question was, how do we ensure everything's updated at once? Oh, you mean the exact opposite. So how do we make sure that everything is updated very slowly? And this is where QD comes in. QD is a holy shit, it's done. I've never seen it this is fast. QD does exactly that. It goes one node by one node, and the thing I actually wanted to show you, but surprisingly, this is really, really fast. So you will see this, you will see individual nodes going from ready into ready scheduling disabled, and then only after all pods evacuated that node, QD will reboot that node, and it'll come up with the new version. And the beauty of that part, which went a lot faster than I intended it to, is that you very slowly see this one upgrading, this one upgrading, this one upgrading. And QD is actually, you can customize QD in a wide amount of options. You can go, if you're adventurous, you can go with more than one node at a time. You can set a threshold for pause between node updates. You can have it very slow, you can have it very fast, basically matching the needs that you have in your cluster. And that's pretty much all I had. I'm done in about 45 minutes. So in today's session, what I wanted to show you is what a systemd system extension is, that it's available on basically all distros. Like you can go there and you can use it on Ubuntu. It'll just work because they ship systemd-sysext. How to build sysext? We didn't really look into that. It's basically, put everything into the subdirectories where you want your files to have, and then run make squashfs on that install root directory, and there will be a file coming out of that, and then that's your sysext. So the question is whether everything needs to be statically compiled. No, it does not. If you remember that part where I showed you the metadata, we can actually go back there. That's a good question. That was in the first demo. So in the first demo, where we interactively explored the contents of that, we have lib extension release, and then for the Kubernetes one, basically matching the file name, the .raw file name. That information, here we use ID any. This is being matched. You can either use ID or version, and this is being matched against information that is in etc OS release, which is part of LSB, which everybody basically ships in their own way. Any is a special case in that it means ignore it. I'm statically compiled. But you can actually bind this to a specific distro and a specific release. So you can make sure whatever you compiled actually runs, because it needs dependencies and all of that. So that works. We don't like doing it because you have traditional packaging for that, or if you need to run independently and still have dependencies, ship a container image. But Flatcar actually ships a few system-dependent sysext. You've seen the Docker and containerd sysext in Flatcar. Those are system-dependent. So there's an actual Flatcar version in the metadata of these files. And the reason for that is runc. Runc is linked against glibc, and we're not taking any chances there. And these system-dependent sysext we either ship directly with the operating system, which is the case for containerd and Docker, or we have a mechanism where you can specify them in a very lean configuration, just one sysext name per line. And then we will download these in the correct versions, release versions, at provisioning time. And we will update these in lockstep. So it hooks into the Flatcar operating system update mechanism. And we will update these in lockstep with the operating system, but we're not aware of any other distro that does that. So the general answer here is better be independent of the operating system. Talking about independence of the operating system, and because we still have a bit of time, I want to point you to the sysext bakery. This is a collection of recipes that build you sysext, and all of these are operating system independent. So you can run these on Flatcar. These can update at their own pace. They don't need to be bound to the operating system. It's got a nice documentation as well. And we have quite a few of these recipes ready to go. We also build them regularly. So the builds of this stuff is automated. It checks whether a new version of the respective item that we ship was updated, is available, and then it just builds a new version of the sysext. And all this stuff is hosted at GitHub releases. So you can just go there, you can download this stuff automatically, and just go ahead and use it. Or you fork this repo and do your own stuff. Yeah, it's well automated. You have a bakery thing, wrapper scripts, and library functions. So you can, when creating sysext, you can focus on the core logic that is special to your system extensions. Right. I'm gonna go and tear down my Azure cluster here. I'm still blown away. Usually, when I arrive at this screen, usually I have one or two of these upgraded because it's a pretty slow process, but it just went there in no time. All right, clean up. So most of the stuff that I'm showing here is available in a repository called Flatcar Demos, which is right here. This demo is largely derived from a FOSDEM talk that I was unable to finish, because back in the day I didn't have just demos, I also had boring slides. I dropped the slides and now I'm in time. So if you look into Kubernetes plumbing, you will see basically most of the stuff what I did here, including the ClusterAPI stuff on Azure. So if you feel like playing around with ClusterAPI, then that's a good starting point. All right. So this should eventually, it's still leading, okay. This should eventually disappear. It's already getting fewer and fewer resources, and then the cluster will be entirely gone. All right. Yeah, so this is how in a very immutable and very without any traces way you can ship Kubernetes, you can install Kubernetes, configure Kubernetes, and update Kubernetes. Any more questions? Awesome. All right. Mathieu and I are here today and tomorrow. We have a booth. Just drop by if you have any questions, comments, or feedback. We just love to talk. And we're basically set up there to do live demos as well, answer questions, dive with you into code. That's what we like to do. Also, if you really liked today and you have, kind of itchy fingers and you want to play with sysext, Mathieu has a sysext workshop tomorrow at 4 p.m. Bring your laptops, And then we're going to dive in, and we're going to do some hacking with sysext. It'll be amazing. You don't need anything else than your laptop and an SSH client. We'll provide the rest for you. Cool. Thanks for attending. And have fun playing with Flatkind with sysext.